lesson. Okay, right. So if you just look at page 39, okay, this is another gravitational field question. So the first thing they start off with is they ask you what's Newton's law of gravitation. So again, this is something that you will see quite often when you do your past year questions. So this one is November 2019 P41. Let me open the solutions. The definition is something that you can find from the notes. All right, it's something that is pretty standard, where we say that Newton's law of gravitation is just where we say that force or attraction between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. Okay. Now, you don't really need to put in the word attraction, but we know that for gravitational force, the forces are always attractive in the first place. Okay. So in your case here, you don't need to write the word attraction here. Okay. The thing that will be given mark is just you saying that the force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. This is where 1 mark comes from. But at the same time, you always need to mention that the force is between 2 point masses. This is where the other point usually comes from. Okay, so this is a pretty standard question. Okay, now if you look at part B will tell you that you have a geostationary satellite that orbits the Earth. Okay, the orbit of the satellite is circular and the period of the orbit is 24 hours. Now, state 2 other features of this orbit. So we went through a bit last time what was a geostationary orbit. In the case for a geostationary orbit for a satellite about the Earth, we say that the satellite always appears to be above the same point on the Earth. Okay, and there were 3 characteristics for your satellite to always be above the same point. The first one was that it must have an orbital period of 24 hours. It must be orbiting above the equator, and it must be orbiting from a direction west to east in this direction. Okay, so it must follow how the Earth rotates in a way. Okay, so here they already told you that your period is 24 hours. The 2 other features must therefore be, it must orbit from west to east, and it must orbit above the equator. Okay, so sometimes rather than saying that the satellite is orbiting above the equator, some marking schemes will say that it follows an equatorial orbit. It follows an equatorial orbit. Okay, it means the same thing. Now, if you move on to the next question, where they tell you the radius of orbit of this satellite is 4.23 times 10 power 4 kilometer. Determine a value for the mass of the Earth and then explain your working. Okay, so this particular question here will be easier if we have a diagram. So this one is our Earth. We say mass big M, and then this one here is our satellite with mass small m. So it's orbiting in a circle like this. They want you to find out what is the value of the Earth. The value for the mass of the Earth. Essentially, they want you to find what is the value of big M. Okay, so explain your working. So in your case, out of the many examples that you have done previously, you know that in your case, the satellite always has a gravitational force of attraction with the Earth. And this gravitational force of attraction is actually providing your centripetal force so that your satellite can move in a circle like this. So when you say explain your working, a lot of times it is always referring to you having to write this statement. Gravitational force provides the centripetal force. Gravitational force is the centripetal force. Only then will you go to Fg equals to Fc. So Fg is Gmm over r square. Fc is mr omega square. And then after that, omega, you try to replace it with 2 pi over t because you have the value of the period in the first place. Okay. So you will get gmm over r squared equals to mr2 pi over t squared. Simplify it, and then after that, sub in your values. The value of the gravitational constant, capital G, is something you can get from your data sheet. And then after that, the radius is 4.23 times 10 power 4. Remember to change to meter, and then remember to cube. And then the rest of the others, you have 4 pi squared. And then your period, 24 hours, change to minutes, change to seconds, and don't forget to square. So eventually, you will get your answer in kg as 6 times 10 power 24 kg. Okay, so this is a very simple example just to refresh your memory a little. Now here you will notice that a lot of times, a lot of the questions you've done so far, we always make use of this fact where Fg equals to Fc. All right, well, there will be one odd or two questions that somehow you will not use Fg equals to Fc. So this one, you will have to look at, I think, page 3 of your worksheet, okay? You won't necessarily always use Fg equals to Fc. There's a certain criterion when you do not need to use it, okay? You look at page 3 of your worksheet, okay? Just look at page 3 of your worksheet. This one is June 15 P42. Okay, so let me just go through that one. June 15 P42 will be this one. Okay, now here we tell you that, maybe I better erase off certain things. We are at page 3. Okay. Now over here we say that the Earth may be considered to be a uniform sphere of radius 6.37 times 10 power 3 kilometer with its mass of 5.9 times 10 24 kg, concentrated as its center. The Earth spins on its axis with a period of 24 hours. You now have a stone of mass 2.5 kg that rests on the Earth's surface and the equator. Now here, they're asking you to calculate using Newton's law of gravitation, the gravitational force on the stone itself. So say for example, you have a stone right now. They say it's at the equator, right? Let me just try and draw it out here like this. You have a stone like this. Okay, that's the equator. And then you have a stone that is situated near the equator. Okay, so here your stone is resting on the Earth. It is at the equator. They want you to find out the gravitational force acting on this stone using Newton's law of gravitation. So Newton's law of gravitation tells you that gravitational force is Fg equals to gmm over r squared. Okay, now you would also have remembered that to find the weight of any object or the gravitational force on any object, you could have just used W equals to mg. But here they don't want you to do that because they specifically said Newton's law of gravitation. So you must use gmm over r squared. So same thing, it's a simple exercise in summing up your values. Gmm over r squared is 6.67 times 10 power minus 11 times mass of the Earth, which is 5.9 times 10 power 24. And then the mass of your stone, which is 2.5. And then divide off by your radius of your Earth, your separation between the masses, between the Earth and the mass, sorry, the Earth and the stone is this R here, which is the radius of the Earth itself. So it's 6.37 times 10 power 3 times 10 power 3 again, because you want to change to meter and then square it. You're going to get the answer is 24.6 Newton. Okay, so this is the gravitational force acting on the stone right now. Now, then after that, if you move on to the next part of the question, they mention to find the force required to maintain the stone in its circular path. Now, the force required to maintain the stone in its circular path, this one by now you should know is talking about centripetal force. Okay, because your stone here, when it's resting on the surface of the Earth, as your Earth is rotating, let's just say like this, because the stone is resting on the Earth, the stone also moves in a circle as the Earth spins about its axis. So we know that your stone is undergoing circular motion. There must be centripetal force to allow your stone to move in a circle. So here, your centripetal force is the force required to maintain the stone in circular path, which you know as either mr omega square or mv square over r. But you would tend to use mr omega square because you know the period, because the omega can be changed to 2 pi over t. So SA is mr omega square, mr 2 pi over t square, then sub in everything that you've done before, and then eventually you get the answer as 0.0842 Newton. Okay, so this is your centripetal force required. Now, part 2 is where it gets a bit weird. If you look at part 2, oh yeah, before I go to that, notice that over here, for question 2, determine the force required to maintain the stone in the circular path. Notice that we didn't just simply say, oh, Fg equals to Fc, therefore Fc was equals to 24.6 Newton. This one we did not do that, okay? In all the previous examples you've done, we always say that Fg is equals to Fc, right? So somehow or another here, you see that if we just simply say that Fg was equals to Fc, so therefore Fc was 24.6 Newton, the answer is completely different with what we found here. This one, we found it by using mr omega square. Okay, so in our current case here, this case, we cannot use Fg equals to Fc. This one I'll explain in the last part of this question, all right? So for now, just remember, this one we cannot use Fg equals to Fc. We have to directly find the centripetal force using mr omega square, okay? Right, so going on to the second part, as I mentioned, the stone is now hung from a Newton meter. Now use your answers in 1, which is basically whatever you found here, to determine the reading on the meter, and then give your answers to 3 significant figures. Okay, right, so they are asking you to find out the reading on your Newton meter. Okay, so you probably would have seen what a Newton meter is before in your lab. It essentially looks something like this. It's something like a spring with some sort of meter in it. Say for example, this one is your weight, and then this one is your Newton meter. It looks something like a spring now, okay? And then that spring is actually contained within some sort of plastic tube, and the tube has some sort of reading onto it. So it tells you the force acting on the Newton meter in Newton, okay? Now, the thing here is this, your Newton meter, a lot of people will always think that your Newton meter is actually measuring the weight, because most of the time what people do is that they go and hang some sort of weight onto the Newton meter, and then the Newton meter will give you a reading, and then you will say that that one is actually the weight of the object that you've just hung, okay? So but the actual case is this, the Newton meter does not only measure weight, it actually measures any resultant downward force. Okay, it actually measures the resultant downward force acting on it. Okay, what it actually is measuring is your resultant downward force. what I mean by that is this. You see, if, say for example, I tell you that your weight that you hung right now is 10 Newton, your Newton meter will give you a value of 10 Newton. But what if somehow or another, when you are hanging the weight of 10 Newton, you suddenly decide to use your hand to pull down onto the weight and you apply a force of say maybe 20 Newton. Your Newton meter is not just going to give you the weight of the load that you just applied anymore. It's going to give you the total force downwards, the total resultant force downward. So your Newton meter, rather than giving you 10 Newton, it will now give you 13 Newton. This is what I mean by the Newton meter. It's actually not really measuring the weight. It's actually measuring whatever resultant downward force is acting on it. Okay, a lot of cases, you just apply the weight only. That's why it's only just giving you the weight. But if let's just say you apply the weight and then you apply another force downwards on it, it will give you the resultant downward force. Okay, so this one, just understand what the Newton meter is doing in the first place. Okay, now here they tell you if they go and hang the stone from your Newton meter, what is the reading on the meter now? In other words, they're asking you what is the resultant downward force currently. So give your answers to 3 significant figures. Okay. Now you notice that this particular question has 2 marks to it. Okay. This particular question has 2 marks to it. It's not as simple as you saying, or the reading on your Newton meter is actually just the weight itself, which was 24.6 Newton. This one is not correct. Okay. You see, if it was something like this, it being allocated 2 marks seems to be very suspicious. It seems too simple to be true to get 2 marks just for a simple statement like that. Okay, so there must be something that you need to realize. Okay, so the thing that you needed to realize is that the Newton meter measures resultant downward force. Okay, that's the reading that you always see. So in your case, if you want to get that reading, you actually need to take the, sorry, let me erase this. In order to get the Newton meter reading, you actually need to take the gravitational force that you calculated earlier, minus all the centripetal force that you calculated after that. So you take 24.6 minus 0.0842, give you 24.5. This is actually your resultant downward force. Okay, because you know that your gravitational force is used to provide your centripetal force, right? But in your current case, your gravitational force was 24.6 Newton, but your centripetal force was 0.0482 Newton. You don't need to use the whole amount of your gravitational force for your centripetal force. There's actually still some balance remaining. Okay, that balance remaining is actually your resultant downward force, which your Newton meter is now measuring. Okay, so far so good. Okay, so then I move on to the next one, but you don't really get it. No, your gravitational, in what sense? No, the Newton meter is measuring whatever resultant downward force you have. Okay. If your mass was not, the thing now is that you originally had a gravitational force of say 24.6 Newton. Okay. But this force, part of it actually went into centripetal force. You cannot measure centripetal force directly using a Newton meter. Okay, so part of it actually went into centripetal force. So there's a balance remaining. This is actually your resultant downward force, which your Newton meter is able to detect and measure right now. Okay, so that's why you need to minus it off, because your Newton meter is measuring your force that is being your force that is pulling the Newton meter down. Okay. But the thing now is that even though you had 24.6 Newton, originally your actual force pulling you down is not 24.6 because a portion of it has been used as centripetal force. Okay. Centripetal force is a different kind of force. You cannot use a Newton meter to register what is your centripetal force. Okay. If I were to think of it another way, this one is actually kind of like your linear force, no? Okay. But this one is centripetal force. Okay. Your Newton meter is measuring the linear force. It cannot measure the centripetal force. So originally you had this force acting down towards the earth, but this portion here, a portion actually went into centripetal force. And then the other balance is your remaining resultant force. Okay, so that's what your Newton meter is actually measuring. So that's the best I can explain now from here. All right. So we cannot just say that it is equals to 24.6. Okay. There is a hidden understanding here that you need to realize. Okay, so that one is okay. Then after that, I move on to the next one. Let me just clear off something. Let me just clear off everything here. Okay, now part B, it gets a bit more complicated. They're telling you right now that a satellite is orbiting the Earth. For an astronaut inside the satellite, his sensation of weight is caused by the contact force from his surroundings. The astronaut reports that he is weightless despite being in the Earth's gravitational field. State what is meant by the astronaut reporting that he is weightless. Okay. So why is it that an astronaut inside a satellite right now feels weightless? Okay, so there's something that you need to realize from here. You notice that they told you here early on that the sensation of weight that the astronaut feels is due to his contact force from the surroundings. Okay, this is actually kind of related to what you learned in AS physics dynamics last time, where we talk about a person standing inside an elevator that is moving will either feel heavier or lighter as the elevator moves. So let me just try and revisit that thing a little. So that time it was mentioned that if let's just say you have a person here, and then I tell you that this elevator is moving up and then it's having an acceleration of A, the person inside the elevator will actually feel heavier because you have weight and then you have you have the normal reaction force. So if I apply F net equals to MA, I will get R minus W equals to MA such that R is equals to W plus MA. So the conclusion then was that the person will actually feel heavier, okay? Because right now, in addition to your weight, you are having weight plus with something else, okay? Now, your sensation of weight is due to your contact force, all right? So the reason why when you're in the elevator, you feel heavier or lighter is because your contact force from the floor is actually changing, okay? Your sensation of weight is due to the contact force from your surroundings. In your case, it's actually from your floor. Let me just write it here properly. Okay, so sensation, okay, this one, don't use this color. Your sensation of weight, or rather your feeling of weight, is due to normal reaction force from the floor. It's due to the normal reaction force from the ground now, okay, from the ground or floor now, which is your R here. And this is what makes you feel your weight. Okay, so this one is where we say that this one, in your case, the elevator moves up, it accelerates, you feel heavier. But what if the elevator moves down and then the acceleration is downwards? What happens to your reaction force? You again still have weight. Sorry, maybe I should eliminate both this one. Moving downwards, okay, still moving downwards. But then now you still have your weight downwards and your reaction force outwards. So again, if I apply F net equals to MA, I will get W plus R equals to MA. But this time my R is actually W minus MA. Okay, so notice that your weight is being subtracted off with MA. MA is being subtracted off from W. You're going to end up with something less than W. So here, you actually feel lighter. Okay, so this is your sensation of weight right now. Okay, so at the same time, that time under the elevator questions, there will also be a certain time where you feel weightless. That one is when your reaction force reaches 0. I can tell you, for example, you're still moving down like this, and then you have your weight downwards, your reaction force outwards, but this time you're actually falling down with acceleration equals to g. So if I apply the same equations, F net equals to ma, I'm going to get W plus R equals to ma, and then R is W minus ma, but W by right is mg, and then since my A is equals to G, this ma will also be mg. So this one will give you 0. So under this case, you actually feel weightless. Okay, this was how we explain your sensation of weight in AS last time. Why you feel heavier, why you feel lighter, why you feel weightless under certain conditions for your elevator motion. So you're trying to apply that same kind of understanding for a satellite right now, for a person inside a satellite. They're asking you to explain why is it that the astronaut inside the satellite is now actually feeling weightless. Okay, so it has to do with Fg being equals to Fc. All right, so let me just draw a diagram here to explain to you why. Okay, so this one is the Earth. Say I have a person here. This is on the surface of the Earth. And then I have my satellite right over here orbiting about the Earth. And again, I have the person on the satellite. Okay. So now, if I consider the two different persons standing on the surface of the Earth and as well as standing on the satellite, they both would have gravitational force, they both would have centripetal force. Okay, both persons are moving in a circle, so they have centripetal force. Both persons are still within the Earth's gravitational field, so they would have gravitational force also. But the relative magnitudes of their gravitational force and centripetal force would not be the same. Okay, what do I mean by that? Let's just say, for example, this one will be at distance r1. I mean, the center to center distance between the person and the Earth will be r1. And then the center to center distance between the person inside the satellite and the Earth will be r2. Okay, so we know that for our case, gravitational force is going to be equals to gmm over r squared. Okay, where we can see that Fg is inversely proportional to r squared. So if your radius increases, or rather your separation increases, your gravitational force will drop. Okay, And then after that, you try to single out centripetal force. Centripetal force can be written as mr omega squared, where we can say that centripetal force is proportional to r, everything else being equal. So in our case, if r increases, our centripetal force actually would increase. Okay, so you see right now, the moment my r increases, gravitational force drops. But when my r increases, my centripetal force will increase. Okay, so the thing here that you need to notice is this. Generally speaking, when a person is standing on the surface of the planet or the Earth, the gravitational force is actually more than your centripetal force. The gravitational, wait, let me just, okay, I think this one is better. Okay, your gravitational force is actually more than your centripetal force when you have a person standing on the surface of the Earth. Okay, so let me just write this out. Gravitational force is more than your centripetal force. There's actually some sort of balance remaining. Okay, there's a balance of downward force remaining, which your Newton meter can measure. This one is what you were doing in part 2. That time I mentioned to you that your gravitational force is more than your centripetal force. You still have some balance remaining there. So that one is what your Newton meter is measuring. Okay. So here, to give you some values, it could be that when you're at the surface of the Earth, your gravitational force is probably, just for the sake of discussion, it could probably be, say, how many? It could probably be, say, 50 Newton for gravitational force, but then centripetal force maybe is 10 Newton. Okay, so you will have a balance of 40 Newton remaining. That is your resultant downward force, which your Newton meter can measure. All right, but as you go further up, if you go outwards in this direction, your R increase, so your Fg would drop, your Fc instead would increase. Okay, so let me write it out properly for you. As you go further out, what color can I use? I'll use green. As you go up, your R increase, but your Fg would drop, your Fc would increase. Okay, so what will actually happen then is that at a certain point when you reach your satellite, and the satellite is orbiting in a circular orbit around your Earth, that point there is where gravitational force equals to your centripetal force. So what you could be having then was that your gravitational force originally on the surface was 50 Newton, but after that, as you keep going all the way up to space towards the satellite, it could have probably dropped all the way to, say, maybe 30 Newton. But at the same time, on the Earth, your centripetal force originally was 10 Newton. As you go further up, the centripetal force increased, it could have probably gone up to 30 Newton. Okay, so in your case, your gravitational force equals to your centripetal force. There's actually no resultant downward force anymore. Okay, the one where you were on the surface of the Earth, this one, there is resultant downward force. But this one, when you're on the satellite, there is no resultant downward force. Okay. So you do not have any resultant downward force. You have your person is no longer pushing down onto the ground, so you have no reaction force anymore. Okay, therefore R is 0. Okay, so just now I mentioned to you over here, if your R is 0, your reaction force from the ground is 0, you are actually going to feel weightless. Okay, so applying it to the case of your person inside the satellite, the thing that is happening here is that when you go all the way up, your gravitational force is actually fully converted or fully providing your centripetal force. There's actually no resultant downward force anymore. Your person is not exerting any force down on the ground. So if there's no force being exerted on the ground, your reaction force is 0. So therefore, this is considered to be weightless. No? Your person will feel weightless. Okay. So maybe I'll add some other statement. No resultant downward force. So no force pushing down on the ground. No force pushing down on the ground. Therefore, no normal reaction force. Okay, I don't have enough space here, but let me just write it here. Therefore, no normal reaction force. Okay, so that's the reason why your astronaut will feel weightless. Okay, so this Fg equals to Fc, as I mentioned, is only when you are at a very large distance away. Okay, all the previous examples you've done so far is Fg equals to Fc, right? So you can only really say Fg equals to Fc when you're talking about a very large separation, when you have an object that is orbiting around the planet itself. And only under those circumstances can you use Fg equals to Fc. But in your current case right now, in your question, you actually do not have the stone, in your case here, orbiting around the Earth at a very large separation. It's actually on the surface of the Earth itself. So when it was on the surface of the Earth itself, Fg is not equals to Fc. Instead, Fg is actually more than Fc here. Okay, that's why you tend to treat it differently in terms of your calculation. You cannot just simply say Fg equals to Fc here because they're not the same in the first place. Fg was actually more than Fc here. Okay, right? So just to get that thing, is it possible for centripetal force to exceed gravitational force? Yes, that is possible. Okay, now you brought up an interesting point. If say Fg, so Fc exceeds Fg, this one means not enough. Just write it properly. In your case here, if let's say your satellite moves too far away or moves too fast now, so that your centripetal force becomes more than your gravitational force, this one means not enough Fg to provide your Fc. So we went through this last time before under circular motion when we talk about a car that moves too fast around a track or when rounding a bend. That time we mentioned that under the case where your frictional force cannot provide your centripetal force, what will just happen is that your car would just move straight off to the straight off at the tangent, right? So it's something similar here also. If let's just say your satellite move too far away, or it moved too fast, your speed increased by a lot such that centripetal force increase, you will not have enough gravitational force to provide your Fc. So at that point, what will happen is that your satellite, let's just say it's over here, it will just move off at the tangent. Okay. So if let's just say your current satellite, for example, I say it moves in a circle like this. If it moves very fast, so that FC increases, so it will come to a case where centripetal force is no longer equal to gravitational force. It's now actually more than your gravitational force. It's more, what is required is more than what gravitational force can provide. So you don't have enough centripetal force. You will not be able to move in a circle. You will just move straight off in a tangent. Okay, so yes, it is possible for your centripetal force to be more than your gravitational force. In such a case, you will not move in a circle. You will just move off from your orbit. You will actually just move in a tangent, move off in a tangent in the first place. Okay, so far so good with that, right? Okay, so yeah, back to the question. I'm just explaining some of the concepts here. Now, if you can get the concepts, and then you should, if you read the answers now, the written answers from your last question, you should be able to understand what is it talking about already. Okay, that's the reason why I needed to explain a long way. I need to give you a long-winded explanation just now. Okay, so if you read the answers, what is meant by the, maybe I better zoom in so that you can see easier. Okay, so in your case here, suggest what is meant by the astronaut reporting that he's weightless. It's a 3-mark question, so some of the things you will need to explain will be something like this, where you say that the gravitational force acting on the astronaut is the one that provides the centripetal force for the astronaut orbiting the Earth. Now, while it is in orbit, when your satellite is in orbit and the astronaut is inside, the gravitational force is actually equal to your centripetal force. Okay, so the contact force, which is the difference between FG and FC, is 0 here. Thus, your astronaut feels weightless. So here, the difference between FG and FC is actually your resultant downward force, which will in turn be equal to your normal reaction force. Okay, so if you have 5 Newton pushing down, your normal reaction force will also be 5 Newton. But if you have 0 Newton, obviously you are going to end up with 0 Newton. Okay, so here, because you already established that gravitational force provides your centripetal force, but while you are in orbit, all the way in outer space, gravitational force is actually equal to your centripetal force instead. So whatever difference between your FG and FC is 0, that one is your resultant downward force. So if your downward force is 0, your contact force will be 0. Therefore, you're actually not going to feel anything. You will actually feel weightless. Okay? Okay. So this is the full answer, explanation to it. The last statement here, therefore the astronaut feels weightless. Actually, you don't need to write this now. This is something that I just write extra so that the explanation feels complete. The answers that I'm given credit are the ones that are highlighted in orange over there. Okay, okay. Also good. Okay, right. So this one is okay. Then after that, I'll just clear this one off and then I'll move on to some other part in your notes. Okay, so we've done quite a fair bit of some difficult questions. All right. So let's move on to the remainder of your gravitational field chapter. Okay, right. We went through gravitational force and we went through gravitational field strength. So let me just recap it a little here. Fg equals to gmm over r squared. G is Fg over m equals to gm over r squared. So we went through these two basic quantities. Now there's also some other quantities that you will need to know when it comes to gravitational field. Now, we need to talk about energy for a mass inside a gravitational field. Now, when you talk about energy possessed by a mass inside a gravitational field, you know that energy as gravitational potential energy. In this chapter, normally is given the symbol U, okay? Now, in AS, we normally define gravitational potential energy is the energy stored in a body due to its position inside a gravitational field, or rather, is the energy stored inside a mass due to its position inside a gravitational field. So, this one was correct at AS level. Okay, if we ask you what's the definition of gravitational potential energy, and then you say this one is okay for AS. But then if we ask you the same for A2, you cannot use that. You use back the same definition. You have to use a more precise definition, which is actually the work done in bringing a mass from infinity to a point in the gravitational field. Okay, so if we ask you in A2, what is definition of gravitational potential energy? It is work done to bring a mass from infinity to a point in the gravitational field. Okay, so why do we say this? It comes from something like this concept. In your AS and work energy power last time, we say that work done on an object is used to increase its energy in some form. Okay, in some form, it can be gravitational energy, gravitational potential energy, electric potential energy, elastic potential energy, or any kind of other energies. Okay, in general, last time in AS physics, we normally told you that whatever work that you do on something normally is used to change the energy of the object. So here you can probably think of it as whatever work you do on an object is used to increase the energy in some form. Let's just say, for example, GPE. Okay, so the idea is this. If let's just say your GPE is 0 at one point, and let's just say at a random point A, and then after that you go and bring it to another point B, you bring it from A to B, it involves work done. Okay, if you were to bring it from A to B, it involves work done. So whatever work that you do would end up being the GPE at this point here. Okay, because the baseline is that you started off from 0 at some point where GPE is defined as 0. If you go and bring it to some other point inside a gravitational field and you do work, whatever work that you've done is actually the GPE at that point. That's why the definition is like this right now, where they say to you, work done in bringing a unit mass from infinity to a point in the gravitational field. Okay, the thing here is that when you are at infinity, your GPE is actually 0. Okay, now there's a common misconception or understanding among people that they say that, oh, your GPE on the surface of the earth is actually 0. Okay, this is something that a lot of people tend to think. If I tell you that this is the surface of the earth, and then you have a person standing here, half the time people will always say that, oh, the GPE on the ground is 0. This is actually not correct. Okay, your GPE is actually not going to be 0 on the ground where you're standing at, because the idea here is that if I tell you that somehow or another a hole suddenly opens up beneath the ground, if a hole suddenly opens up beneath the person will actually still fall into the ground, right? Okay, so that person still falling into the ground implies that there's still changes in GPE. So GPE cannot be 0 here, okay, because you still can move down So you still can have changes in GPE. So you can still have changes in GPE. This one cannot be considered as 0. All right. So you may also be thinking that, oh, the center of the Earth is where GPE is 0. This is also not true. Okay. GPE is not 0 at the center of the Earth also. Neither is it 0 on the surface of the planet or on the surface of the Earth. Where GPE is 0 is actually at infinity. Okay. Where you are talking about distances at infinity, your GPE is actually 0 there. Okay. Now, the reason why we say GPE is going to be 0 at infinity is because at infinity, there is no gravitational force. Okay. So remember last time when you're talking about work done is force times distance, right? So there needs to be a force. There needs to be a force to have work done in the first place. To have work done. Okay. You need to have force in the first place to have work done, because the equation for work done is W equals to Fs, right? Or W equals to Fd in some textbook. Okay. You need to have force in the first place to have work done. So here, if you recall that Fg is gmm over r square. Sorry, let me just write this properly. If you recall that Fg is gmm over r square, what happens if r is at infinity? So if r is at infinity, this one is basically you dividing by infinity. Your Fg would actually be 0, isn't it? Okay. So at infinity, you actually have no gravitational force. So when you have no gravitational force, it also means that you have no capacity to do work. Okay, wait, let me just get rid of this. You have no capacity to do work. Therefore, GPE will be 0. This is where your GPE is 0. Okay, it's at infinity. Okay, so your GPE at infinity is 0. All right, so that one is your reference point. Okay, at infinity. So if let's just say I tell you right now, this is planet Earth, and then this one is at infinity, and then I'm interested in the GPE value at some point here. By definition, the GPE at this point will be whatever work that I do to bring a mass from infinity to this point. Okay, so whatever work that I do to bring the mass from infinity to this point will be my GPE at this point itself. That's what this definition is trying to tell you. Okay, right? So another thing that you should probably know is this. When we're talking about GPE values would always be negative. Wait, let me just clear off everything because it's a bit messy. Now, when you're talking about GPE values at a particular point, GPE values at less than infinity will always be negative. Okay. Now, there's a reason why we say that GPE values will always be negative. Okay, you can look at it in a number of ways, in two different directions actually. So what do I mean by that is this. Say for example, you have a mass at infinity right over here. This one is already established that GPE is going to be 0. Okay, and then this is the point that we are interested in, whose GPE value we're interested in. Now, if you bring a mass from infinity to this point, you can think of it as this. In the first place, if let's just say the mass at infinity here goes slightly out of position from infinity, you will start to have a gravitational force, isn't it? So the thing here is this. if you already have a gravitational force, if let's just say you just nudge the mass a little away from infinity, you're going to have a gravitational force acting on the mass. Okay, so if you already have a gravitational force acting on the mass will actually move by itself from infinity to this point, because the gravitational force itself is actually pulling it from here to here. The thing here is that you do not need to purposely apply a force to push the mass from infinity to here. So in your current case, we will actually say that going from infinity to this point, going towards the left, work is done by the mass. Okay, the mass itself is doing the work. You are not doing work on the mass. Okay, so one way to know whether it's work done by mass, you can just think of it as no external force applied to move it. No external force. Wait, small mass. Okay, yeah, I forgot to mention. You bring a small mass from infinity to this point. Okay, the big mass here remains as it is. It doesn't do anything. This mass, big mass, is the one producing your gravitational field. Okay, but I'm interested in the gravitational field at this point. Inside the I'm interested in the gravitational potential energy at this point inside the gravitational field produced by the big mass. Okay, so right now I go and use a test mass right now. The test mass is my small mass m. Okay, the test mass is my small mass m. So I'm trying to bring the test mass from infinity to a point inside the gravitational field. So because by definition we know that gravitational potential energy at a point is whatever work that you did to bring the mass from infinity to that point. Okay, so if right now, but after that I told you that GPE will be negative, right? Okay, so I'm trying to explain to you right now why is it that GPE values is going to be negative if you're talking about distances less than infinity. All right, so back to what I was mentioning. If you bring a mass from infinity to this point, by right, there's already a gravitational force acting on the mass. You don't need to purposely apply any external force to bring the mass from infinity to this point. Okay, so no external force applied by anyone. Work is actually done by the mass. So when work is done by the mass, what we'll tell you is that GPE will decrease. Okay, if work is done on mass, GPE increases. But if work is done by mass, GPE decreases. Okay, so this one is what's happening right now. If you're going from infinity, work is done by the mass, GPE decreases from 0, because here is 0, right? So you go towards the left, GPE is decreasing in value. So obviously GPE will be negative in value. Okay, that's why we can say that for 1, GPE is going to be negative. Actually, kind of explain it over here. Yeah. So if mass is brought from infinity to a point in gravitational field, what is done by the mass since gravitational force pulls the mass towards the other larger mass, thereby decreasing its GPE. And since GPE is 0 at infinity and GPE is decreasing, moving away from infinity, the resulting GPE value must be less than 0. In other words, GPE is decreasing from 0 lah. So your GPE must be negative in the first place. Okay, so if you think of it as that, GPE value must always be negative. Now, you can also think of it the other way around also. What if I don't bring a mass from infinity to that point? Instead, I did it the other way around, where I tell you I bring the mass from that point all the way to infinity. Would my value still be negative? You will actually get back that same conclusion. All right. Now, but in your current case now, it's a bit different. Slightly different. You need to modify it. If you're talking about at this point, you already definitely are going to have a existing gravitational force here, pulling the small mass, the test mass, towards the big mass. Okay, Now, if you wanted to bring this mass all the way to here, there's already an existing gravitational force trying to pull it in the opposite direction. If you had wanted to push this mass all the way to infinity, you would actually need to overcome this gravitational force in the first place. So in your case, you actually need to purposely apply an external force to overcome this gravitational force so that you can move the mass from this point all the way to infinity. Okay, so it's because of this that we will say that when you want to go from here to infinity, work is actually done on the mass. Okay, work is done on mass. Okay, so when work is done on the mass, GPE increases. Okay, but in your case, it is increasing to GPE 0. It's increasing to 0. GPE increases to 0. So how can you have a value increasing to 0 in the first place? That is only possible if GPE value was negative in the first place. Therefore, GPE is negative also. Okay, right? You can explain it in two different directions. Either you bring the mass from infinity to that point, or you either bring the mass from that point to infinity. You will still get the same conclusion that GPE value is going to be negative. Okay, so when work is done on the mass, this one we say that external force is applied to overcome the gravitational force. Okay, so this is why I know this is work done on mass, because I had to purposely apply a force in order to move it. And when I purposely apply a force in order to move it, I'm actually doing work on the mass. So whatever work I do on the mass is increasing its GPE value. But it so happens that in your case, it's increasing to 0 right now. So GPE value must be negative. Okay, so this is what the other statement is actually saying. Conversely, if a mass was brought from a point in the gravitational field towards infinity, work is now done on the mass to overcome the gravitational attractive forces, thereby increasing its GPE. Again, since your GPE is at infinity is 0 and GPE is increasing towards infinity, your GPE value must be 0 in the first place. No, sorry, your GPE value in the first place must be less than 0. In other words, negative. Okay. I think probably I should write this now. If it's less than 0, that means negative value. Okay. So GPE values at any point less than infinity will always be negative. That's why here we'll tell you, if you want to find GPE values at any point, you just use this equation, and that equation has a negative sign to it to tell you that GPE value is negative. Okay, so you want to find GPE values at a point, you will need to use equation U equals to negative GMM over R. Okay, the negative sign here is meant to tell you that GPE values is negative, like what I've just explained to you. Okay, so when you do calculations involving GPE, always make sure to put in the negative. The negative sign is actually pretty important. Okay, because gravitational potential energy is a scalar quantity. Okay, it does not have any direction, only value, only magnitude. If you have any negative sign, it is already an indication of your value, not direction. What I mean by that is this, maybe it's a bit confusing for you. If I tell you this now, I tell you for vectors, 5 Newton versus negative 5 Newton. Automatically, you will tell me that this one is actually acting in the opposite direction, right? Okay, so for the cases of vectors, negative sign is just simply telling you it's just acting in opposite direction. But what if I tell you for scalars? I tell you, say 15 degrees centigrade versus negative 15 degrees centigrade. You wouldn't tell me that this negative is just saying that temperature is acting in opposite direction, right? This is actually just saying that it is actually this negative here, you won't associate it with direction. Instead, you associate it with value, or rather how hot something is now. How hot something is, isn't it? So 15 degrees is considered maybe warm. Negative 15 degrees is considered to be very cold. Okay, so the negative here isn't telling you direction. It's actually telling you a measure of its value. Okay, so for scalars, like gravitational potential energy here, the negative sign is quite important. You need to put it in, all right? And this negative sign is actually not an indication of direction for a vector. It is an indication of value. Okay, so far so good with that, I hope. Okay, right. All this is something like just basic understanding to it. You won't really be tested on it. I mean, okay, it's just something to help you understand better so that later on when you do the questions, it makes more sense to you. All right. Okay, now another thing that I should probably mention to you is this. Just now it was mentioned to you that the GPE value at a point is actually the work done to bring a test mass from infinity to this point, right? So sometimes people will say, okay, if that's the case, GPE is actually equal to work done. Can I just say that it is force times distance, where in my case, the F is my gravitational force, and then my S is basically my R, the distance moved from here. Okay, maybe I little not use R. My S is this one. Okay, from infinity to this point. Now the answer is you cannot do that. All right. Because some people will say, why is it that my GPE value, I need to specifically use GMM over R? Why can't I just use Fs, where I say that F is the gravitational force, S is your distance move from infinity to whatever point that is. Now, the thing here is this. Last time in AS, when you guys wanted to use work done as the product of force times distance, there was a condition to use this equation. That one being F must be constant. Okay, F must be constant in the first place for this equation to be valid. Now, in your current case, when you are bringing a mass from infinity all the way to your point that you're considering, notice that your R, the center to center distance between the masses, is actually varying. Gravitational force is GMM over R squared. So Fg is actually inversely proportional to R squared. So if you bring your mass from infinity to a point, whatever point that is, your R is actually not constant. Therefore, your Fg is also not going to be constant. Okay. So the fact that your force is not constant in the first place automatically would mean that you cannot use this equation. You cannot use this. That's why I wrote that in the notes somewhere in the next page. Work equals to force times distance cannot be used to derive the equation that you see, which is this one, because force is not constant here. Okay, we cannot use that. All right. The actual way that they got the negative GMM over R was actually through this. They actually use integration from infinity to distance R, where they say is GMM over R square dr. Okay, So there's a derivation for it. To get the GPA at a point, we know that it's work done to bring a mass from infinity to that point. So, but because the nature of the force was not constant, we cannot use W equals to Fs. Instead, we have to use integration, where we say we integrate the function of gmm over r squared from infinity to r with respect to r. Then we will eventually get this. Okay, if you do the integration, you will actually get this. Okay, this is the actual way they got the expression for GPE at a point. Okay, but this one, the derivation is not required in your syllabus now. You're not really required to know how to derive the expression. You're not really required to know the derivation for GPE. All you just need to know is that if I'm interested in GPE at a point, the GPE is just negative gmm over r. Okay, right? So that is just one thing to know lah. Okay, so all these are just extra information, but the gist is that you really just need to know this equation. That's all. Everything else is just extra information. Okay, now if I'm interested to find the GPE values between 2 points, I will just take the difference in GPE between those GPE energy between those 2 points now. Okay, where in my case, for example, let me just draw something here for you. If this is my big mass M, and then this is 0.1, and then this one, sorry, these are the 2 different points. This is say 0.1, and then this is say 0.2. I'm interested in the GPE values between these 2 points. What's the change in GPE between these 2 points? So at point 2, the GPE value by right is negative gmm over r2. At point 1, the GPE is negative gmm over r1. If I want to take the difference in GPE between the two values, this one will be u1 minus u2. Okay. Generally, take the higher value minus the lower value. Okay, but when you go and sub in your values to find the difference, don't omit out your negative. Okay, please make sure the negative sign is still there. Okay, so just something to take note of, right? I think I mentioned this also in AS physics. I'm not sure whether I mentioned for your class. To find changes in scalar quantities, such as energy, always take higher value minus the lower value. Okay, so in my case, I'm taking changes in GP between 2 points. I would tend to take the higher value minus the lower value. U1 is actually higher value. Okay, wait, let me just write. Okay. This one, U1 will actually be higher value. U2 will actually be lower value. Okay. Now, because of this, you see, this one is say R2. This one is say R1. You can think of it as this now. Why is U2 going to be having a lower value GP? Because it's at lower height. This is the easier way I can mention to people. Because see, this one is at a lower height compared to this one, right? U1 is a higher value because it is at a larger height. Because this is something like what you guys learned last time in AS. If something is a smaller height, your GP is lower. If something is at a larger height, your GP is higher. Okay, so you can just think of it as that. Generally, the larger your height, the larger your GPE. Okay, so this one, maybe I better make my term more consistent, smaller height. Okay, right? So this is one thing to note. To find change in GPE, just use this. Okay, now you may be wondering also, last time in AS, we found change in GP between 2 points by using equation mg delta h, right? Okay, now the mg delta h that time is only for small distances less than 1000 meter, where g remains constant. Okay, so we know that g is actually negative g, sorry, not negative, there's no gm here, there's no negative here, this gm over r square, right? Where we say that g is inversely proportional to r square. So in general, if your r changes a lot, your g will change a lot. Okay, so last time in AS, we tended to use this change in GP equals to mg delta h. That one was okay to use because the distances involved was just less than 1000 meter, where the field strength is still approximately constant. But when you're talking about the current chapter, where your distances involved is very, very large, all the way into outer space, which is definitely more than 1000 meter, your G is not constant anymore. Okay, it will continuously vary. So we cannot use this equation from AS. In AS, we can, because G is already can be assumed to be constant due to the small distances involved. But in A2, because of the distances involved being very, very large right now, G is no longer constant. We cannot use that old equation. Okay, so we have to use the previous one, this one. This one is actually the more accurate one. Okay, so that's just one thing to note. Okay, yeah, I think it's probably a lot to take in. There's just one small part here before I think I can kind of finish this chapter. Okay, now there's also another different quantity called gravitational potential. Okay, previously you learned gravitational potential energy. Okay, the new term that you're seeing here is just the same thing but without the energy. It's just called gravitational potential. Okay, now gravitational potential is kind of the same as gravitational potential energy, just that it's per unit mass. Okay, now when you see this little symbol, this is actually not theta. Okay, it is not the symbol theta. It's actually a Greek symbol called phi. Okay, theta is written like this. Phi is a circle with a line across it like this. This one was theta, this is phi. So gravitational potential is usually denoted by the symbol phi. Okay, so the definition for gravitational potential is that it's similar to gravitational potential energy, just that it's for per unit mass. So gravitational potential can be defined as work done in bringing a unit mass from infinity to a point in the gravitational field. So if you try to write it down in equation form, this means that this means that gravitational potential is gravitational potential energy divided by mass. Because you see, if you look at these two statements itself, work done in bringing mass from infinity to a point in the gravitational field, this one was already the definition of U, or rather GPE. If you suddenly add per unit mass, it means U divided by M. Okay, that's why it says GPE, but in terms of per unit mass. Okay, so phi is U over M, but at the same time, you know that U is negative GMM over R. So you sub in inside the equation, you will notice that the small m will actually cancel each other off, giving you phi equals to negative GM over R. Okay, so for gravitational potential, you can actually have two different equations. Either phi is U over M or phi is negative GM over R. All right. So Same thing like before, gravitational potential will always have negative sign to it because its value is always less than 0. Okay. Then the last thing I should probably mention to you is this. Now, in addition to finding change in gravitational potential energy between 2 points, we can use this equation. We can use, when we want to find change in gravitational potential energy, we can use this equation. There's also another simpler equation we can use, which is this one, where we say that change in GP between 2 points is actually the mass times the change in potential. It actually came from this, where we said that this equation here, phi is u over m, right? Where we can say that if phi is u over m, u is m phi, but u was actually my GPE lah, okay? Now, GPE is m times potential. If I go and introduce the change symbol inside, I will get delta GPE equals to mass times delta phi. This is how this equation came about. It's actually from the definition at the top. Okay. GPA at a point is the mass times the potential at that point. But at the same time, I can actually modify this equation to give me change in GP between 2 points is actually the mass times the change in potential between the same 2 points. Okay. So this is gravitational potential for this one. All right. Okay. So that one is okay. Okay, now there is one last thing, escape velocity. Let me just go through that. Let me just go through this and then we're done with the chapter already. And after that, we can start doing some of the questions. So let me just clear off everything here. Okay, now, so the next last thing that you will need to learn is something called escape speed. Okay, escape speed is pretty straightforward. Now, when we want to launch a satellite from a planet, let's just say, for example, this is our planet here. We want to launch some object far off into outer space. It could be a satellite, it could be a rocket, it could be anything. The thing is that generally when we want to launch an object out into outer space so that it never returns, the object must be launched with a certain minimum speed called escape speed. Okay, so if that object is launched with a speed less than this escape speed, it will never be able to escape from the gravitational field of the planet that it is on. Okay, you always need to have a certain minimum speed called your escape speed in order to be able to escape all the way into outer space. If you don't have that, gravity will just pull your object back towards the planet itself. Okay, so what you're interested to find out is what is this escape speed, VE here. Okay, so when you want to derive the escape speed, there's actually just a simple conservation of energy principle that you need to apply. You consider two different spots. Let's just say a spot on the surface of the planet that you're launching it from, and at infinity, which is the place that you've already escaped to and not returned. Now, it was really mentioned to you before at infinity, your GP value would be 0. Okay, and then on the surface of the planet that you're launching from, your GP ought to be negative gmm over r. All right. Now, what about the KE then? If you're talking about the KE, on the surface of the planet that you're launching from, the KE will be half mVe squared, where VE is your escape speed. But at infinity, your KE ought to be 0. Okay, now why do I say that the KE would be 0 here? It is due to this fact. You see, when you launch anything, say for example, say you launch a rocket or a satellite, okay, and it moves all the way to infinity. Let's just say that this one is here is infinity. Okay, your direction of motion is here. Okay, this is your direction of motion, but you are still under the influence of your gravitational field. You're still being pulled by gravity. where gravity is pulling you in this direction. Okay, so if you consider this, your motion is towards the right, but your gravitational field is towards the left. Your gravitational force, sorry, your gravitational force towards the left is in the opposite direction. What this would mean to you is that you would actually start to slow down, okay? As you move towards infinity, you will actually start to slow down. So it will be reasonable to assume that if, let's say, you were moving with an initial speed of VE, escape speed, as you go all the way towards infinity, you will start to slow down until such a point that you reach 0 meter per second at infinity. That's why your KE here is going to be 0. Okay, so maybe I just write it here. You go here, you will slow down. Okay, so these are the two. That's why I can say that your KE here is going to be 0. All right. So when you go towards the infinity direction, you will lose kinetic energy because you slow down. That's what I mentioned. At the same time, you will gain gravitational potential energy because there's an increase in height from the surface of the planet. Okay, so now if you try to apply conservation of energy now, let me just write some stuff here. This one is you slowing down, therefore KE drop. This one is you increasing height, therefore GPE increase. If you apply conservation of energy over here, you will get the gain in GPE equals to loss in KE. Okay, so in my case, my gain in GPE will be 0 minus negative GMM over R, giving me GMM over R instead. Okay, 0 is the higher value compared to negative GMM over R because 0 is 0, negative GMM over R is a negative value. Okay, so I take the higher value minus the lower value. So I will get GMM over R. And then after that, when I talk about the change in KE, it's just half MVE squared minus 0, giving me half MVE squared. So just now I told you that the change in KE is equals to the change in GPE. The loss in KE is equals to the gain in my GPE. I sub those equations in, I sub what I just found, I will be able to get half MVE squared equals to GMM over R, where eventually VE is actually square root 2GM over R. Okay, so this is actually the escape speed. All right, so I think I'm going to write it out for you. Change in GPE is change in KE in one shot. So this one is 0 minus negative GMM over R equals to half MVE squared minus 0. So this one will give me GMM over R of MVE squared. So VE is negative square root 2GM over R. Okay, so this is your escape speed. Now, your escape speed has a very similar form to something else that you just learned in this chapter. If you look at the next page, under the satellite orbits case, you notice that you also have another equation which also relates to speed, where we say that V is square root G over square root GM over R. Okay, so this one is square root GM over R. The one that you're seeing is square root 2 GM over R. The form seems to be similar. The only difference is that there's a 2. But those two are talking about two different things entirely, okay? Your square root of 2 GM over R is talking about escape speed. What's the speed that your object would need in order to escape all the way to infinity? The other one you see in the next page, square root GM over R, is talking about linear speed for a satellite or object that is moving in circular orbit around another planet. Okay, so there's a difference between those two. Well, although I'm talking about speed, they're actually talking about a different kind. One is linear speed, one is escape speed. Okay, so they're actually two different things altogether. All right. Now the rest of the notes here is actually just telling you that your equation VE square root 2 GM over R can be changed to another different expression where it's square root 2 GR. Okay, this one you make use of the equation G is GM over R square. So if VE is square root 2 GM over R, you multiply with R over R, you're going to get 2 GM over R squared times R, where this one itself is G. So that's why you get this. But I would say this one is actually not so important, okay? Because I've never seen in your past year where they ask you to use this equation or where they ask you to express it in this equation, in this form, okay? This one I don't think is really that important. What is important is the one at the top.